Great. Well, thanks so much, Take, and thanks all of you for being up early for this talk. It's yeah, I'm really looking forward to it. I know I'll talk in part of my talk today. I'll talk about some work that's come out of a center that I direct, and I know that for you being with the WPI, you understand the power of collaboration and bringing together people that have complementary skills and interests, and that I think you'll definitely see that, or at least I hope you will in the talk today. So what I would like to talk about, I'll set up this way, which is if we think about the polymer-based materials of the past, present, or future, we tend to think of them as fulfilling a structural role, right? And if you ask yourself, like, what kind of chemical reactivity would you like those materials to have? In general, I would say historically, the answer has been as little as possible, right? You would like to just have that material stay exactly as it is in terms of its chemical composition. If on the other hand, if you ask, for example, the internet, right, what does chemical reactivity look like? Well, it's kind of bubbling, colorful liquids done in flasks in a laboratory. And the point is that there's no structural activity to any of that. Right? And in my lab and in the center I direct, Monet, we're really interested about the intersection of those two things and kind of asking the questions, are there opportunities to be gained by embedding chemical reactivity into structural materials based on polymers? And the stories, there are a lot of ways you could think about that question and answer, but today I'd really like to focus on some examples built around the concept of the mechanophore. And for those of you who aren't familiar, let me introduce this with an example. This is an example not from my lab, but from Jeff Moore and Nancy Sotos, although a grad student of mine put this movie together. So the molecule that you see here is called spiropyran. It's got this central carbon atom with 4 substituents on it. And the key point here is that now I can take a reaction of interest, in this case, the dissociation of that carbon-oxygen bond, and I've embedded it along the main chain of a polymer in a way that if I applied tension and stretch that polymer chain, it couples on to the reaction of interest. In this case, homolytic carbon-oxygen or heterolytic carbon-oxygen bond breaking, right? So I've broken that bond, but otherwise in this case left that functional group along the main chain. Now, there are a couple of consequences of that reaction. The first is that the polymer chain has actually grown longer as a result of that rearrangement. And the second is that I've opened up a conjugation pathway in the molecule here so that it becomes colored. And that allows us to actually visualize that reaction occurring, in this case, in a little rubbery silicone that is cross-linked by that spiropyran mechanophore. Okay, so this is just one example of a mechanophore in action. There are other examples, some of which I'll talk about today. In this case, that reaction is reversible. Other cases, they can be irreversible, can not just change color, but emit photons of light or release reagents into the surroundings. Okay, and so because the mechanical forces or the forces between my fingers are many orders of magnitude larger than the forces between atoms, this concept in principle sort of allows you to think about doing anything. And I'll give one example of what I mean by that here. And that's in terms of this difluorocyclopropane mechanophore, that if you pull on these adjacent positions in the ring, what occurs is what we see experimentally is consistent with the molecular dynamics simulation that I'm showing here in the movie. that cyclopropane ring will now open to a 1,3 diradical, where it's essentially trapped under a high force of tension. And the cool thing about this is that diradical that's now stable under force is actually the transition state of a very high activation energy chemical reaction. In this case, the inversion of stereochemistry around that ring. But here it becomes a new global minimum on the force-coupled potential energy surface. So we've sort of taken this transient, impossible to trap structure and now trapped it under these very, very high forces of tension. Okay? And so, if we can do that, right, then there must be many other things that we can do. And that realization has, over the last almost 2 decades now, I would say, spurred a lot of very creative work by chemists from all over the globe. And the point of this slide is really just to communicate that, not any specific examples here, but a number of groups have done really, really beautiful work in this area. And mechanophores now are, kind of pop up in a lot of different contexts, including very sort of heterogeneous bulk systems, single molecules. Sometimes the forces applied are very high and held for long periods of time. Other times they're just experienced for, maybe as short as microseconds in the case of collapsing sonication bubbles. And one of the fun things about working in this field is that even though these are very, very different environments, the principles that unite the molecular response and the kind of chemical reactivity that can be created are very much the same in general to all of these settings. So what I would like to do today is to basically try to answer 3 questions. The first is, so how do I really think about reactivity in these systems? And then given that reactivity, how might I use it to redefine some of the performance limits of polymeric-based materials? And then if there's time, and I want to be very respectful of everyone's time this morning, I'll maybe pose the question about some opportunities for using material platforms to manipulate reaction pathways in ways that might actually be useful. Say it's relaxed evening here on the Duke campus. I know it's early morning there, but I've got the little chat box open. If there are questions along the way, please feel free to ask. I would rather have things make sense and not get through all the slides than get through everything and have it be confusing. Okay. So let's start with this first question about kind of fundamental aspects of the reactivity that's involved here. Okay. And I like to illustrate this in the context of a mechanophore based on cyclobutane, right? And the specific reaction here of interest would be to break this cyclobutane in half into what the chemists in your WPI would recognize as a pair of alkenes. And the way that I like to think about this reactivity is that now I've taken this reactant and essentially I've coupled it to a spring under tension, where the spring now represents for us often overstretched polymers, right? That are being stretched, for example, in a material. So applying that force does a couple of things. The first is that it distorts the reactant, right? Starts kind of tugging it away from its equilibrium structure. That's typically a very minor contribution to the reactivity. The main contribution comes from the fact that now I'm doing mechanical work in a way that is coupled to the reaction path. And what I mean by that is that if I go from this ground state structure of the cyclobutane to a transition state of the rate determining step, in this case, breaking that very first carbon-carbon bond in the cyclobutane, that as my chemical potential energy changes and goes up of the cyclobutane, the mechanical potential energy in my spring goes down, right? Because now the spring can relax a little bit as the reactant gets longer. And so, and if that spring relaxes by a distance, say delta X here, then the energy that needs to go into the reactant from thermal fluctuations goes down by force times that distance, F delta X. And I can relate that change in activation energy to an expected change in essentially the logarithm of the rate constant here. Okay. So just a couple of points about that is in this picture, there's still a thermal barrier. Okay, so the force isn't just pulling things immediately, right? It helps accelerate the rate, but there's still a barrier to the reaction. And if you ask the question, how much force is required for a given reaction to occur, the answer depends on how quickly you need that reaction to occur, right? So the faster the rate constant that you want, the more you need to lower the activation energy, the larger the force you need to apply is through this distance and this that I'm referring to as delta X here. Okay. And one of the nice things is we can actually quantify that reactivity. So in my lab, we have a couple of home-built atomic force microscopes. And we set up experiments along the lines where we'll trap a polymer between the tip of the AFM and another surface, and then pull it. And into that polymer, we embed not just one mechanophore as shown in the cartoon here, but many, many copies, tens or even in some cases, hundreds or thousands of mechanophores within a polymer chain that we're sampling. And so the picture is that you pull that chain, as you stretch it, the force increases until you reach a force high enough to trigger reactions on the time scale of interest. And then we see that reactivity occur through a plateau in this force extension curve, okay, until all the reactions are done, and then you just kind of stretch the chain. And one of the nice things about this experiment is that because I'm collecting data in real time, I essentially know how many reactions have occurred as a function of time and force. So I can get rate constants for these reactions as a function of the applied force. And a few years ago, Xu Wang and Brandon Bowser in the lab wanted to characterize the force-coupled kinetics of breaking cyclobutanes, like I showed a couple of slides ago, apart now into a pair of alkenes, right? So the product of these reactions are these alkenes. And the way they did this was to design polymers that had many copies of either type 1 or type 2 cyclobutanes with either these aryl groups or just a little methylene alkyl spacer here, put them into polymers, but did it not, so they wanted to understand how these cyclobutanes would break. But in order to do that, they wanted to see many of these events occurring. And so they tied the bottom half of the cyclobutanes together in a large macrocycle, so that now opening up one ring, breaking one cyclobutane would just allow the polymer to grow longer. And when they do the AFM experiments in collaboration with Tatiana Kuznetsova, who's sort of the world leader and a very member of my lab that I'm very, very grateful to have. What they saw was the expected extension plateaus, and they see very clearly that the mechanically coupled reactivity is quite different, right? That if I have these aryl groups on those cyclobutanes, the force required to get that cyclobutane to break apart is much lower for the time scales here, which are around 10 to 100 milliseconds or so. Okay? And that's consistent with what we know about the reactivity in these systems, right? That the rate determining step is the breaking of that initial carbon-carbon bond. And with those aryl groups there, they essentially stabilize that radical character by resonance. So the bottom line is all of this data makes sense. If you're skeptical that this is really what we might be seeing, I think further evidence comes if you go and zoom in on these force extension curves. When you do that, what you see are little sawtooth patterns in that force extension curve. And if you look and actually measure how far apart are the features in these sawtooth patterns, well, there's a little bit of noise there, but basically they're 3.4 nanometers apart from each other. And that 3.4 nanometers matches with almost embarrassing precision what molecular models tell you should be the gain and extension for each individual cyclobutane ring opening reaction. So we feel very, very confident in this data. And then we can take these AFM data and go back and get rate constants by kind of doing them at different rates and in different contexts, get rate constants as a function of force. What we see from that is the expected log linear relationship between the rate constant and the force that we're applying. And again, I'll just make the point here that there is no one single force at which the reaction will occur. There's just a force that determines a lifetime, essentially, of these two cyclobutanes. And so now we have that well characterized. Okay, and I'm going to take these mechanophores, these cyclobutanes, and use that characterized reactivity as the basis for the next story. Okay, so bottom line here, same kind of kinetic and mechanistic principles that we're familiar with from chemical reactivity. Now we've just added this coupled force to the picture. Mm-hmm. And so the second part of the talk, I'd like to focus on this question of what happens if I take that kind of force-coupled reactivity and embed it into polymeric materials. And this is work that was done in collaboration with several of the other groups that are in MONET, the Center for Molecularly Optimized Networks. Okay, and the basis for this, and part of why I think it's such an interesting question, is that if you ask questions about the physical limits of polymer materials, right, we tend to either look at them historically through the lens of mechanics, right, sort of taking what we know about bulk stress strain behavior and using like kind of continuum mechanics, finite elements modeling that I'm sure many in your center are familiar with, and use those to kind of understand the how tearing and fracture occurs, right? You can also answer that question from a physics point of view in the case of polymer networks. Think about network topology and bridging strands and overstretched force chains within networks. But ultimately, I think there's another level here, right? Because these behaviors really do translate back to molecular behaviors. And so mechanochemistry, for example, things like the spiropyran that I showed earlier, right, where you get color turning on, has been successfully used to probe physics, to probe mechanics in polymer-based systems. But we're really interested now in the question of, does that mechanochemical response within a material actually influence its properties? And if so, to what extent? Okay. And let me just give one first example of the kinds of questions that I mean by that. Right? So Xu Wang, working with me and Michael Rubenstein here at Duke, collaborated with Haley Beach, then a graduate student at MIT with Brad Olson, to do the following experiment. They took a tetra-armed polyethylene glycol kind of star polymer, right? So a polymer with 4 branches and reactive end groups, these azides at the end of each of those branches, and then reacted them with a difunctional alkyne through what is the chemists will recognize as a copper-assisted azide alkyne coupling reaction. The point being that the end of one branch would react with one of these groups, and the other group would act with the end of another branch and sort of stitch the whole thing together into a network that now we investigate as essentially a gel swollen in propylene carbonate. And in between, in the middle of this end linker, right, Xu built this cyclobutane mechanophore that I've shown you before, with the understanding that tension applied through these connections could break that cyclobutane, now not to release stored length, because I don't have the macrocycle at the bottom, but just to literally split it in half at forces and with probabilities that we have characterized in our single molecule experiments. And then Xu and Haley did this exact same process to make gels, but did it now with two other end linkers, one with the even more reactive diaryl cyclobutane, and then a control that has no cyclobutane or in fact any other especially reactive group built into it. They do all of these under identical conditions, making polymer gels that are identical except that they have embedded within each of the elastically active strands of that network a group that is either very mechanically reactive, a little mechanically reactive, or not especially mechanically reactive. There. And then ask the question, okay, what does that embedded reactivity mean for the mechanical limits of the polymer? In order to answer that question, Haley made bulk films in this way, put a little notch, so essentially started a crack in those films, and then stretched it in the up and down directions as shown here until that crack would start to propagate. And so there's sort of a measure, right? The more you have to stretch it in order to get the tearing to really take off, the crack to start moving through the material, the stronger, the more resistant to tearing your network is. And what Haley observed was, right, as she stretched, that's the x-axis on the bottom here, the force would go up, that's the stress on the y-axis, and it would go up and up and up until you would tear the network, and then it goes down. And what she observed time and time again was this very nice correlation, right? Where the weaker, the more reactive the mechanophore, the less tear resistant the polymer network, the more reactive or less reactive the strand, the more resistant to tearing. And you can actually quantify this, right, in terms of sort of an energy per area required for the tearing. And what you see is that changing the reactivity here from most reactive to least reactive gives you about an order of magnitude difference in the tear resistance in these materials, right? So that's a pretty large effect. It's large enough actually that I've done the blind test myself in the lab, gone into lab, and I can tell which of these networks is made from which material, right? And it all is coming just by embedding a single mechanophore, a single reactive group into each of the polymer chains. Okay. Of course, most of the polymer networks that are interesting to us and that are around us in our day-to-day lives don't look like N-linked polyethylene glycol. Right? Most of the polymer materials that we really care about, right, look like essentially what you can think of as sort of a melt of long linear polymers, right, that, for example, on their own would have no appreciable mechanical properties, right? So the things I'll talk about next would be just sort of thick liquids, kind of like honey, almost, but maybe even a little more fluid than honey. So very, very poor mechanical properties. The way we get good mechanical properties out of them is to randomly cross-link them, not at the ends of every chain, right? But just kind of at random places pendant to the main chains, right? So off of the side chains. And to make that, usually what we do is we use, like if we're doing a free radical polymerization, you will use a bifunctional cross-linker, right? With just kind of a conventional carbon and oxygen-based linear group in between, like the one I show here. The networks I will talk about are polyacrylates. They're made from this methoxyethyl acrylate shown here. So they're room temperature rubbery, kind of like a rubber band, if you will. And the polymers and networks that are made here are made through what's known as a controlled radical polymerization. So this is, for those who are familiar, this would be a raft polymerization. The important piece of that is that we can control the length of the gray strands within the polymer network. Okay. And so Xu then went and asked the question. So he could make a kind of conventionally cross-linked network with kind of the normal, strong, non-mechanophore cross-linker, and then make another network under absolutely identical conditions but now with the diaryl cyclobutane. So this was the most reactive, if you will, the weakest or the weaker of the two mechanophores I showed previously, and ask, is it still an order of magnitude? Is it still sort of a factor of 10 difference between these two networks, or is it even greater? Is it less? How do they compare? Okay. And so I'll now show a movie of one of these characterizations experiments in action. So these are now the two networks, one made with a control, sort of the conventional crosslinker. That's the kind of crosslinker you would normally find in a polymer network. And the other is cross-linked with Xu's mechanophore. These are the two now elastomers, so there's no solvent, right? So it's very much like a rubber band. It's just the solid material here, cross-linked. These two films now, again, are identical, but they're now clamped between, hopefully you see two clamps, bottom and top, and then she was put a notch, right? Kind of started a crack on the left side of each. And now I'll play a movie and it'll be just like essentially pulling the top clamp away to watch, and you can watch and see how those cracks propagate. Right? So now the movie started, and what you see is that now the crack on the right is immediately taken off. The one at the left, it takes a lot longer for it to get started. This is constant displacement, so time is a nice surrogate for strain. And even when it starts tearing, it tears much more slowly. Okay, so the movie here is just on loop. This is all the same experiment over and over again, but we've repeated the experiment many times. We've sent samples to collaborators across the country. They always see the same thing, that there's a huge effect here. We can quantify the tearing energy again. Again, it is about a factor of 10 different, but as you undoubtedly have noticed, is now in the opposite direction. Okay, and so I'd just like to, well here, and I'll just say, done this not just with this polymer, with other polymers, done it in gels as opposed to elastomers, looked at, cyclic loading and fatigue. We always see the exact difference between the mechanophore and the control depends a little bit on the conditions and the polymer, but qualitatively, we always see this, okay? And it's the opposite direction, right? So what I'm telling you is we've taken this polymer melt, right? That itself is like a liquid that basically doesn't even tear, right? Because it just flows, okay? To make it a solid with some resistance to tearing, okay, we cross-link it. And if you cross-link it with something that is strong and hard to break, you get a material that's easy to break. And if you cross-link it with something that's easy to break, you get a material that's much more difficult to tear. Okay, so why is that? Right? I'll be honest, it's not what we expected, right? But Xu saw this, and his interpretation, his hypothesis was, okay, here's what I think's happening. It says, if I'm the conventional network and a crack is trying to go through it, then everything in front of the crack looks the same. Okay? And so what determines where things break molecularly in the kind of the classical picture is just where are the sites where a little piece of the network gets stretched to its limits first. That's the thing that's going to break first, and that's what determines how the crack moves through the network, how tearing happens. On the other hand, now if I've put a mechanophore in there, I'm really a composite at the molecular level, right? I've got these long primary strands. They're strong. They're just conventional carbon-carbon bonds. But now I've cross-linked them through these very reactive, mechanically reactive cyclobutane cross-linkers. And so on an event-by-event basis here, maybe the crack doesn't just go where the tension is greatest, it goes where the reactivity is greatest, where the response to that tension is the most sensitive, right? In other words, it tries to go around the polymer chains instead of through them, if you'll allow me to anthropomorphize a little bit, right? And while each individual event is easier, that kind of adds up to make tearing more difficult because there are many, many more events you have to go through. I will say that some simulations by our computational colleagues support this picture very well, but I actually like Shu's experimental evidence for it. Because what he did was he took advantage of this controlled radical polymerization and made networks in which he changed the length of the gray strands. And I've highlighted one of them in red here just to accentuate it, right? So some networks he makes with very long strands and others with shorter strands, which you could sort of think of as being what you would have gotten if you just went through up here and clipped, snipped a few of those strands randomly throughout the network, okay? So when he does that, what he sees is that the control networks and the mechanophore networks, they look the same, they swell the same, they have the same modulus, how much force it takes to deform them at very low strains. The difference comes when you now start trying to tear them, okay? If you try to tear the network made with sort of the normal cross-linker that you would kind of find in commodity polymers, for example, how long the primary strand is doesn't matter, okay? They all look the same. And this is why usually when people make polymer networks, no one ever asks, how long are the primary strands in your network? They just ask, how many cross-links do you have? That's what really determines the limits here. But when you cross-link now, and so left to right are longer primary chains in the networks. When you do the identical networks, but now cross-link with the mechanophore, what we see is a huge dependence on that primary chain length, right? Consistent with Shu's picture that when we have the mechanophores in there as cross-linker, the crack is trying to go around those chains. So the longer the chain is, kind of the further around, if you will, the crack has to go, okay? So sort of the big take-home message here, and one we continue to pursue within the center, is that the very details of topology, and I know you're a group that likes to think about topology on different levels and in different contexts, right? But that can have a huge impact on modulating and even, in fact, reversing the effect of incorporating mechanophores, whether they make the material stronger or weaker, and just how much they do that. Just like to point out that these huge differences in tearing energy that we observe are the only time that we so far have been able to see any meaningful difference in these networks. If we characterize, so if there are any kind of polymer folks in your network, if we characterize dynamic mechanical properties, they look the same. If you're not familiar with that, the important thing is that the red and the blue dots here, circles, lie on top of each other, okay? That means that mechanically, again, so if you had a mechanical function for the conventional material, the material with the mechanophore could fill that exact same function and you would never know the difference, except it's harder to tear. get asked a lot about, well, if it's easier to break these cyclobutanes, don't you like see some hysteresis and that makes the material wear down more easily? Actually, quite the opposite here, right? So what I'm showing here are stretching the material out to close to its limits and back many, many times. And these lines lie on top of each other, stretching it to by 70% of its original length, 73, 76, 79%. Back and forth, the slope of those lines doesn't change after many, many repeats of it. At 80% or just a little bit over, that's where the material breaks. So we're going almost up to its limits. This is with the mechanophore, and can't see any influence from mechanophore breaking. It's very, very small amounts. It's it has a very minimal impact on properties here. And the conventional control, I will just say, breaks down here at around 30% strain, less than half of what we see with the mechanophore. Again, right? So that's like complete loss of properties where we see absolutely none with the mechanophore here. Okay. So happy, love talking about this, would be delighted to talk more if anyone is interested, but the big point is we really do need enough mechanochemical reactivity to redirect that molecular fracture. And one of the things I like about Shu's design here, right, is that it shows that you can get the necessary mechanochemical reactivity while still keeping enough thermal stability that otherwise it's just staying intact and functional in all the ways that you would want that structural unit to fulfill. Okay. And having this ability to keep kind of normal properties the same, but change how hard it is for things to tear or to wear down, for us in the center makes us think about problems like tire wear, right? Which isn't just I would say, sort of a consumer problem, but really a global environmental problem. In part for these large, huge tire graveyards that you see, but even more significantly, just for the amount of microplastic that's released into the environment is really kind of staggering from tire wear, right? Tire engineers can tell you how to make a tire that wears down more slowly. The problem is that there's a trade-off, right? The tire that wears more slowly compromises things like safety and fuel efficiency and performance, right? Things that we also care about a lot and that can have huge environmental impacts on their own, right? If you think about fuel efficiency, right? So we're excited by the possibility of embedded reactivity in the form of mechanophores, essentially rewriting some of the rules of trade-offs in materials and seeing if there might be fundamental knowledge we can uncover that could translate up to problems maybe even as great as this. One of the things that I like in my lab and we in the center is that once you start thinking this way, new ideas start popping up, right? So Zi Wang in the lab several years ago kind of asked the what if question, like what if I had a mechanophore that didn't break, but was more like the mechanophores we use in our AFM experiments, right? That would, when the reaction occurred, it would take something that starts as a short polymer chain and turn it into a much, much longer polymer chain. What would that mean for network properties? Okay, so Z developed some very nice chemistry that allowed us to embed large quantities of kind of strain releasing stored length mechanophores into polymer chains. Okay, with the idea that I could take that chain and under force it would grow longer. And so here's the specific transformation, is again breaking a cyclobutane here, not to break the chain, but to form now a couple of alkenes held together by this fused ring, right, which now opens up to increase the length in the main chain. And then as a control, he could make identical polymers, okay, but now with a cyclobutane that doesn't have a ring fuse, just has a couple of substituents, so that now the polymer chain would break at a point where this polymer chain starts to grow longer. And I won't go through all of the details here, but Z kind of figured out the chemistry to make hydrogels out of these. These are actually double network hydrogels. And so the important thing is that the stress-bearing part of these materials has on the left polymer strands that Z had made to grow longer. And on the right, the polymer strands that Z made to break at the point where the ones on the left grew longer. And so I'll now again show these two otherwise identical hydrogels being stretched. We'll pick it up midway through because it's a long test. And to just for entertainment value, one of the fun things about having our center, at least, is that we have a music director who writes pieces of music based on some of the research we're doing, and then we give these public performances where we do the music and then a short talk about the science for a general audience. So I'll let David Ibbett, our music director, accompany this with a piano piece he wrote. So what you see is that the gel made out of strands programmed to break has now broken, whereas the gel made out of strands that could stretch further can be stretched further until finally it breaks as well. Okay, so we can go back, we can characterize these two types of polymers in our single molecule experiments, both the ones that break, shown in red here, or the ones that grow longer, shown in blue. So we kind of know the force at which they start to grow longer. We know how much longer they get. We can actually calculate at the single molecule that they absorb about 3 times more energy before they break. And that leads to hydrogels, right? So we've got chains that can grow about 40% longer. We've got gels that can be stretched 40 to 50% further. The chains absorb 3 times as much energy. The gels are twice as hard to tear. And again, just like the kind of with the randomly cross-linked networks, these hydrogels as well have actually less hysteresis under cyclic loading than their conventional counterparts. Okay, so that's part 2 here. In fact, yes, embedding mechanically coupled reactivity can actually change the kinds of properties that we get out of these materials. And then Take, I'll take advice from you. I could tell one more story in about 5 minutes, or I could just go ahead and take questions.
Just go ahead. Yes, we have plenty of time. So.
Great. All right. Then I'll do that. And so this last story will be essentially about taking that concept and turning it around the other way, about using the polymer network to try to influence chemistry that happens. And this is work done in collaboration with my colleague Ross Wiedenhofer here at Duke and Roman Bulatov at the University of Liverpool. And shown here is a postdoc in my lab, Shujun Zhang, who has really made this this story that I'm really excited about happen. Okay, so there are a lot of catalytic reactions that will give you a mixture of excuse me, of products. For example, like RNS stereoisomers and enantiomers that come out, right? One example is the rhodium catalyzed hydrogenation of alkenes, which can be done in a stereoselective manner to give either of 2 mirror image chiral molecules, right? So here now we're just thinking about structural chirality at the molecular level, not sort of not the kinds of electronic consequences of that chirality that I know your center is thinking about a lot. The root of that chiral preference in these reactions is using a chiral ligand that coordinates to the rhodium, and that sort of dictates the product distribution that you get. And that distribution of products, of course, depends very much on conditions, right? So if you wanted it to get better, you might change the solvent, the temperature, maybe the pressure, change the shape or structure of the ligand, or even the metal that's involved here. And we can do that to optimize. Oh yeah, sorry, I should have taken some questions. So I tell you what, maybe can I come back to this question at the end, since I apologize, I've already sort of started on the reactivity thing, but I'll hit that very, very first. Okay. And so the sort of the question that we've been asking more recently is, can I use strain in the material to change the nature of that enantioselectivity? Okay. And Shujun thought that this would be a very nice reaction to test that concept on, because he showed using small molecules and using essentially force in the form of intramolecular tension in a strained macrocycle. This is work done with Roman Bulatov, who's figured out how you can sort of computationally figure out the relevant force here, to show that as a force of attention on that ligand goes up, the enantioselectivity, so ER here is the enantiomeric ratio of R to S, goes up again in sort of a logarithmic dependence on force, in the same way that the chemical reaction rates I showed before went up logarithmically, or their log went up with force, so went up exponentially with force. Okay, so he asked the question, could I figure out a way to get that to translate to bulk materials? And so a lot of trial and error, right? He figured out, he kind of made this this ligand crosslinker now, right, which is going to go into the network in a way that tension in the network would come down to the ligand and sort of couple onto its chiral, the axis of chirality along that ligand. I won't go into the details of sort of the recipe for that network. It wasn't the first thing Shujun tried, or the one we ultimately used wasn't the first one he tried, but what he found has worked very nicely. And so what he would then do is take a network that has this ligand coupled into it, kind of swell it as a gel with reactants in it, put it into a clamp, could stretch the clamp now to strain the gel, and then take that whole clamp, drop it into a little reaction vial, and now you could run a reaction and measure just like a baseline enantioselectivity where the gel was not stretched at all. And then start straining the gel. And as he strained the gel, what he saw was, depending on how much he strained it, the enantioselectivity of that reaction improves, gets a little better, strain more, it gets better yet. And then if he takes it and returns the gel back to its initial state, that enantioselectivity goes back down to its initial value. He then made a control system where the ligand is not coupled to tension, but is just on the side chain, sort of dangling out in space in the polymer. And now there's a negligible dependence of enantioselectivity on applied strain. You can see the same thing, not just in tension, but in compression. Again, the more you kind of squish it, the better it gets, and then it'll relax back to its value if you kind of take the strain off there. Okay, so we're really excited about this concept of multi-state mechanocatalysis, not just for selectivity, but for reactivity and rates. We're looking at device architectures that will allow us to apply even larger forces to materials without tearing them, and maybe to do so on rapid time scales. And even though the effect so far that we see in the bulk is pretty modest, right? So the best Shujun has seen is to go from an enantiomeric excess of 35% to 65%. So full disclosure, right? The chemists in the audience here aren't going to be blown away by that. There are other ways you can get to better EEs. But what I will say is these materials are heterogeneous, and a lot of work and other observations we've made in other products really suggest that the bulk of the catalytic sites in there aren't changing much, if at all, right? What's really dominating the effect here are a few very privileged sites that are, you know, going up to essentially quantitatively selective enantioselectivity in those reactions. And it's just we need to find out kind of architectures and designs that allow us to really zero in on those. Okay. So with that, I've sort of told you what I've told you. I've tried, but undoubtedly failed to give credit to the people who've done most of the work, right? And so of the many things that I haven't told you, I think the most important is just how amazingly fortunate I am to work with such great students and postdocs. Thank you all very much. I'd be happy to take questions however you see, but perhaps I should I guess start with the one in chat. Take, I'll take my lead from you at this point.